simply because he couldn't see them, were blocked out. So how did astronomers determine how big the galaxy actually is? So they eventually, through mapping out various regions of the sky, astronomers discovered that some stars were varying, what they called variable stars. And these variable stars turned out to be quite useful for getting the size of our galaxy. So I'll explain why. So first, let me explain what a variable star is. It's essentially just a star that has a periodic luminosity, meaning that the luminosity or the brightness of the star changes over time and in a very systematic way. And there are two types of these variable stars that were identified. The first type that we'll mention are called the RR Lyrae. That's just named after the first star like that was identified. And if you look at this figure here, it shows how bright the star is as a function of time. So you can see that the star is just kind of pulsing here. It gets brighter and then fainter, brighter and then fainter. It has a kind of weird little wiggle in there too. So if you saw this happening, you'd be able to characterize a star as being like RR Lyrae. All RR Lyrae stars pulsate in a similar way, and they have periods of about half a day to 1 day. So that means this increase, this peak position here, is the difference between that is the length of time from one bright position to another bright position, and we call it the period. And so the periods for RR Lyrae are relatively short. Okay, so there was another kind of variable star identified called a Cepheid, and it was also named after the first star like that was identified. Usually you see like there's some constellation names here that tells you in which constellation that star was first found. Now look at the Cepheid light curve. It has a brightness over here versus time, but what you notice about it is the shape of the curve looks a little bit different and it's more stretched out. So what's happening for a Cepheid is that the period is a lot longer, and generally they can range anywhere from 1 to 100 days. So RR Lyrae have periods of usually less than a day, and Cepheids were usually a lot more than a day. Anyway, astronomers found that these different kinds of stars in the sky, and okay, that's interesting, very nice, but how does that help us understand the size of our galaxy? We'll get to that in just a minute. But first, let's talk about why those stars are doing that. This is a little bit weird, right? Most stars do not do that. They don't vary their luminosity on timescales that short, nor do they do it in a regular way like that. So clearly there's something happening to these stars physically in their life, in their evolutionary stage. And in fact, if we put these stars on the HR diagram, you remember from the last couple chapters where we plot temperature here and brightness over here, remember here's the main sequence, these variable stars are all up in this kind of dark gray strip here that we call the instability strip. Now, the instability strip is named so because stars that are in this part of the diagram happen to be unstable, meaning that they cannot find equilibrium. So remember, a star is always trying to kind of find a balance between the exterior weight of the star pressing in and the rate of nuclear reactions in the core that are pushing out. So it just so happens that when stars are in this particular part of the diagram, they have difficulty finding that balance, and the star becomes internally unstable. And that means that the temperature and the radius of the star can vary in a regular way, causing a physical pulsation. So the star is physically pulsing, getting smaller, larger, smaller, larger, and that's changing its luminosity. And you can see that the stars in this part of the diagram, some of them can be very, very luminous and some not as luminous down at this end. So the Cepheids, turns out, these stars are up in here. They're the most massive stars that are going through the instability strip. They're primarily high mass stars that are evolving across the top of the HR diagram. When I say that, what I mean is that, remember, these stars are going to sit on the main sequence up here, very quickly burn their fuel, and move across the HR diagram until they ignite the next element, and they go back over here, and they kind of go back and forth up here. And every time the star goes through this instability strip, it does have a period where it pulsates, and it would be called a Cepheid variable at that time. Now, RR Lyrae stars, they're the lower mass stars. They tend to be sitting right about here. And this is about where that horizontal branch is located. So remember, the horizontal branch is the place where stars are burning helium in their core. So it just happens that some stars that are burning helium in their core also have difficulty finding equilibrium, and they will pulsate, and these are called the Our Lyrae variables. Now, what's lucky about these types of stars is that there's this relationship between the pulsation period of the star and its luminosity. You probably could sort of tell that because we talked about how Our Lyraes, we said, well, they're sort of the lower mass stars, and they have these shorter periods, less than a day. Cepheids are these higher mass stars, and they have these longer periods. And what you'll notice is that these kind of like this trend here among the Cepheids extends down here to Our Lyraes and shows this relationship between period and luminosity. So these higher mass stars are also more luminous, and the more luminous you are, apparently, the longer the pulsation period. So astronomers determined this relationship between luminosity and period. Now, why is that helpful? Well, it means that if you know the period of the star, you can then know its luminosity. Once a relationship like this is calibrated, of course, you have to initially get the distances to
Don't
some of
worry
the
about
stars
this too
probably in
much.
parallax. And when you have that, then you know their luminosities. Once this relationship is known, then all you got to do is get the pulsation period, right? And that's something you can measure from your telescope pretty easily. And, oh, okay, here's a star with a 10-day pulsation period. Okay, it must be this luminosity, right? Because it has to fall in this relationship. And so that's great. Once you know a star's true luminosity, then you can get the distance because of this relationship between apparent brightness or flux, luminosity, and distance squared. So variable stars add another rung to our distance ladder up here, allowing us to get out to, well, we can actually even get to some nearby galaxy distances if we find these bright Cepheids there, but definitely allow us to get distances to sort of more remote parts of the Milky Way galaxy. And that's really helpful because we want to try to figure out how big our galaxy is. But the Cepheids are so bright that some of them can be seen in nearby galaxies, and we'll mention that in a little bit as well.